If you haven't watched my videos that prove these formulas for product rule and quotient rule by using the limit definition of a derivative, I strongly encourage you to do that and see where do we get these formulas. If you're taking the derivative of the product of two functions, f of x times g of x, then our product rule will be f of x times the derivative of g of x plus g of x times the derivative of f of x. Another way you can kind of shorten that is to say f dg plus g df. The d means derivative of. So f dg plus g df, f dg plus g df, f dg plus g df. Say that 10 times over and you'll be on your way to memorizing the product rule. For the quotient rule, if you have f of x over g of x, you take the denominator function times the derivative of the numerator function, minus the numerator times the derivative of the denominator function, all over the denominator function squared. So I like to call the denominator low and the numerator high. In that case, our formula is low d high minus high d low over low squared we go. And I've got a special little song for that. Low d high minus high d low over low squared we go, over low squared we go. Low d high minus high d low over low squared we go, over low squared we go. So let's differentiate. Notice that we could avoid the product rule by just expanding these two quantities and then using the power rule. But for this video, we're going to practice product rule. We have our first function times our second function. The product rule is f dg, so the derivative of g with respect to x, and I'm not going to derive that yet. I'll leave that for my next step, plus g df. The derivative of 2x plus 3 is 2. The derivative of 3x squared minus 2 is 6x. Let's expand and combine like terms. That's our derivative. Again, you could use the power rule for this, but we're going to practice using the quotient rule. Low d high minus high d low over low squared we go. Low d high minus high d low over low squared. Again, I like to do the other derivatives in my next step. Hey, the derivative of 9 is 0. There's our derivative. Plug it into the formula, low d high minus high d low over low squared we go. Check to see if you have any common quantities. No, you do not, so we're going to expand and combine like terms. Now we'll combine like terms. There's my derivative. Time to evaluate a second derivative of a quotient. Let's start with our first derivative. Low d high minus high d low over low squared. We go. This derivative is 2x plus 1. This derivative is 1. I don't see any common quantities between these two products, so I will expand and combine like terms. You may think that the top can be factored, but unfortunately it cannot. So this is our first derivative. Now it's time to derive again. This is where we get this notation. Time for the quotient rule. Let's evaluate those derivatives. Now we haven't learned how to derive this yet, so let's expand and use the power rule. That's a perfect square trinomial. And that derivative is equal to 2x minus 2. Now x minus 1 is to the quantity of 4. At this point in time, I see that this product has a 2x minus 2, and this product has a 2x minus 2. So I can factor out the quantity 2x minus 2. Factoring out means dividing, so you've divided this product by 2x minus 2, and you're left with x minus 1 squared. When you divide this product by 2x minus 2, you're left with negative quantity x squared minus 2x minus 1. How does that help me? Well, 2x minus 2 can be factored further. We can take a 2 out of that. Now we can expand the things inside the brackets. So why was factoring x minus 1 out so important? Because x minus 1 over x minus 1 to the 4th does reduce. You get x minus 1 to the 3rd in the denominator. Let's combine our like terms. X squared minus x squared, negative 2x plus 2x, and 1 plus 1 is 2. This is the second derivative. When you use the quotient rule twice, you're probably going to have to factor not only a number, but a quantity, like we did here with 2x minus 2. Always look for ways you can factor so that you can continually reduce and make it as simplified as possible.